The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
My name is Josh Messner, and welcome to Titans of Nuclear. Today, we have the honor of chatting with Dr. Wayne Solomon, who is the Vice President of Magnetic Fusion Energy at General Atomics. Wayne, welcome to the show.
Hi, Josh. Thanks so much for that introduction. Thanks for having me here today. I appreciate the opportunity.
Super excited. So we always like to start with a bit of a background on our guests. So let's start with, where are you from? Tell us about Wayne as a child growing up.
Sure. Well, I don't know, maybe you can tell from my funny accent that I was born in Australia, in Sydney. I lived there for the first 6 or so years of my life, and I moved up north with my family to a place called Brisbane. You may have heard of it. It's in a state called Queensland. I guess at a young age, maybe like many people who end up in science and technology fields, I really was fascinated by math and science from an early age, even though, frankly, there wasn't really that kind of interest or enthusiasm within my immediate family or even my extended family. I guess in later part of high school, I was selected to be part of our national squad for the Physics Olympiad. And
oh, very cool.
I had the opportunity then to see fusion research at our Australian National University, ANU, it's affectionately referred to sometimes. And I thought this was amazing and a world-changing type of thing that I'd love to be involved with. And I guess the rest, as they say, was history. During that time at the Olympiad, I also really enjoyed later helping to create some new pathways for students to kind of get interested, who are interested in physics,
Sure.
Trying to get into this, working with some of the other physics Olympiads to kick off like a junior physics Olympiad program in Queensland. And so I guess, with that intense interest locked in for physics, I did my undergraduate studies at the University of Queensland. Then I went back to the ANU and did my PhD, and I ended up coming to San Diego about 20 years ago for my postdoc with the Princeton Plasma Physics Laboratory, but coming out here to work at DIII-D at San Diego General Atomics. And that's the largest fusion experiment in the US. I really felt passionate about devoting my time and effort to helping to realize fusion at this point, and was, because, really can provide near limitless energy to the planet. And, DIII-D was really the natural place to do that kind of research. And honestly, that was a great time for me. I was employed by one of the preeminent national labs, working at one of the preeminent devices, living in sunny San Diego with my bosses on the other side of the country. So, what's not to like?
There you go. No, I'd love to go back a little bit. Like growing up in Australia, I mean, I'm not too in tune with nuclear, with Australia's nuclear climate, but I know it hasn't been a perfectly straight course since about the 1950s. However, I mean, you guys have what, the second or third highest uranium deposits behind Canada, Kazakhstan? Yeah. So tell us a little bit about studying nuclear at that time in Australia.
Yeah, well, as you say, so nuclear is an energy source. Now we're talking nuclear fission, of course.
Of course.
That, there's none of the power really is generated in Australia by fission, but we have those reserves, and the country as a whole is happy to sell those resources for other countries that are interested in using uranium for nuclear power. And so there isn't much of a nuclear program, but of course fusion, especially then, but even today, is largely driven by on the physics side, plasma physics, and so there's, you know, they're kind of really quite separate in space for training and background, and, you know, just even public perception about what the two are. And I think I see a lot of that in the US too now as well. I mean, you know, there's quite a big divide, I think, between the perceptions and the baggage, if you want to call it that, associated with fission and sort of the promise and hope of fusion.
Mm-hmm. Yeah, I think most people probably remember the kind of treaty that was signed a while back about nuclear submarines in Australia, and like that is their extent of nuclear in Australia. It doesn't go
That's
beyond
pretty
that.
much it. That's
Yeah.
pretty much it. Yeah.
So you find yourself in sunny San Diego. Tell us a little bit about, yeah, some of your first roles at GA.
Yeah. So when I was here as a postdoc, I was doing research early on in some ways was connected to the stuff I was doing in my PhD. So I was studying basic plasma transport turbulence, how that affects how energy escapes out of the plasma.
Okay.
One of the key ways that you can improve the confinement of a fusion grade plasma is through rotation. So the way the plasma spins, and you can think of it simply as, you know, if you have the plasma rotating at different rates at different parts of the plasma, then you create kind of like a shear layer. And if you imagine these kind of turbulent eddies, then having this kind of shearing process splits apart and makes those eddies much smaller and makes it harder for the turbulence to take that energy out of the plasma. So my early research here at DIII-D was really focused on trying to understand rotation, what mechanisms can lead to it. And there's a whole fascinating realm there. I mean, you might think, well, you know, momentum, rotation, that's all pretty straightforward, right? Conservation of momentum. But even in a tokamak environment, you have these funny situations where the plasma can spontaneously appear to spin out of nothing. And I mean, you can explain it still in terms of those fundamentals,
Sure. Okay.
But you can, you know, you get these effects which we call intrinsic rotation, and you can have this even if there's no obvious momentum input, and it just has to do with the way that if you look at the distribution of those particles, some of them are going in one direction, some of them going in the other direction. You know, there's a way that some of those particles might be lost, and then the ones which are left have a preferential direction in a, you know, that leads to a net rotation. So it's really cool, and so the plasma has ways of even generating its own rotation that can help with this improvement in confinement.
And are you noticing, I'm just curious about this kind of phenomenon. Are you experiencing or noticing those in some of the complex simulations that you're running ahead of actual, okay. And
Yeah.
do those line up with what could or is happening kind of in real life, or are you seeing stuff that is like disassociated from the simulations that you're writing? Yeah.
Well, I think one of the things that's really been a key advance overall in fusion is the ability to, you know, carefully simulate all these different aspects of the plasma. And I think when, you know, intrinsic rotation was first discovered, it was a bit of a head scratcher, and theorists, you know, got to work. They maybe dusted off some ideas they'd had before, and you know, so it's quickly, I would say it was relatively quickly understood, and then large scale simulations were able to reproduce these. And I would say the case isn't maybe fully closed, but I think there are enough different models and ways of explaining it that, yeah, we can capture this understanding.
Very cool. So I don't want to jump too far ahead, but you're at like a 1-year anniversary right now of your new role.
That is basically
as
right.
Vice
Yes, that's true.
President.
That is true. Yeah.
So yeah, before we jump into that and the exciting projects that you're working on, I'd love to just reflect on your previous, you know, number of years at GA. What are some of like the notable projects? Sounds like this rotational one project. What are some of the others?
Oh yeah, well, I've had a very interesting time at my time at DIII-D and General Atomics. So I've sort of, after working on sort of what you might call it some more fundamental physics understanding, then you have to realize that fusion and, you know, the experiment that we run is really a whole integrated type thing. Like what you do in one to deal with one particular issue has an impact on maybe the confinement, or has an impact on the stability, or impact on the heat that's coming out of it. So it's very tightly coupled. And so I found myself moving into looking at sort of whole scenario optimization, but still with an interest of rotation and so, you know, I mentioned that rotation has an impact on the confinement. And so we'd long learned how to, even without these detailed understanding and simulations, we'd understood how to exploit that to make the tokamak bigger, and then better. And then you start realizing, what do these processes actually translate as you go to what might eventually be a commercial fusion power plant or a next step device. And so it turns out that some of these things don't scale necessarily well. The ability to rotate the plasma gets harder, perhaps. And so you start looking at that and what is the impact on those. So we did a whole you know, range of scenario development, trying to get all of the benefits that we'd learned from you know, rotational shear improvements on confinement, but finding other knobs basically that can give you the same type of effect, and things like the way you craft the magnetic profile, the current profile, all of these type of things all can give similar types of benefits. And so we kind of worked on this for several years. And I also, you know, I've worked on parts of the plasma to try and improve. So, you know, we have different modes of confinement, and one of those is called H mode. It's like it stands for high confinement mode, and it's characterized by something that we refer to as a pedestal. That's because you've got this very thin insulating layer between the very hot core and what ostensibly becomes a room temperature, you know, the metal walls. And so there's this very thin insulating layer where the confinement is very high, the temperature gradients are very strong, and there's all sorts of interesting instabilities that happen there, and we have to try to figure out how to control those instabilities as well. And so that was another part of that process of integration. How can you get high confinement and maintain those instabilities without ejecting all of this heat and particles to the wall, which could damage the wall? So like I said, it's just very integrated.
Yeah, you turn one
challenge.
dial and 80 other dials are messed up, and you got to turn those dials and come back. Yeah,
exactly. But I think over time we've really got a good handle on how to do all of these things, and so it's really been, you know, fun to watch all of this come into place.
Absolutely. Before we go further, I'd love for you to just give us a kind of layman's description of what is a tokamak. Like, can you give, like, for the average listener, what is that, and what does it stand for? I hear it's kind of like a conglomerate of words or phrases.
Yeah, well, it actually is a Russian acronym. I'm not sure if I can remember the exact. But basically, the devices, you can think of it as, so okay, let's go back to like fusion. Which in magnetic fusion, what we're trying to do is recreate the process of the sun, right? So the sun does fusion every day. That's what we're trying to do in the lab every day as well. So the tokamak is a device that we have that basically uses strong magnetic fields to try to confine this very hot, what starts off as a gas but enters into what we sometimes refer to as the fourth state of matter, a plasma, right? And these, you know, this hot plasma, when you get it really hot, of course, you can overcome the electrostatic repulsion of the nuclei, and that's what lets you to get to fusion. And a tiny amount of mass is converted into a tremendous amount of energy. This is just, you know, realization of Einstein's famous E equals mc squared equation. And so the tokamak basically is a device that provides this magnetic field. There's a series of what we call toroidal magnetic fields. So these are basically field coils that go around the outside of the vessel and provide the major component of that magnetic field. But it's a little bit more complicated than that, because if you only had this one direction of magnetic fields, it turns out that you find that the plasma will basically drift out of the top or the bottom of that device, even though it's wrapped around into a torus shape, like a donut. So we have another component of the magnetic field that we provide through a central solenoid. Basically, we drive current in that central solenoid. It's like, you can think of it as like the secondary coil of a transformer. And so we ramp the current in that central coil there, and that provides a changing flux and induces a current in the plasma, and that provides like another component of that magnetic field. So the tokamak really is that device that provides that magnetic bottle, if you like, for containing the plasma. And into that bottle, then we have to inject heating power to get the plasma hot enough to get into fusion relevant conditions, and do various things that we would like to do to control that plasma, whether it's through adjusting the exact details of the magnetic field, or the current, or the rotation, or all these different control actuators that we have as well. So that if you like is the tokamak.
Absolutely awesome. I really appreciate that. So can you give me maybe a bit of a history of the DIII-D facility?
Sure. Yeah, well, DIII-D, as the name maybe slightly alludes to, is a one in a series of tokamaks that actually started out in a configuration called a doublet, which is really kind of something to do with what the shape looked like, let's put it that way.
Sure.
And that doublet was really the first D in that DIII-D, what it stands for. And actually, if you walk through our machine bay today, you can still find pieces of doublet 1 and then doublet 2 and doublet 3, which was sort of the succession of devices that were built of increasing size to test the scaling of this particular concept. And I guess between about 1984 and 1985, doublet 3 was converted to the machine that we now call DIII-D.
Okay.
And which was then affectionately referred to as Big D, reflecting the change in the vacuum vessel and the plasma shape, which was made at that time. And that actually was the final D in that DIII-D. And so that change was really driven by some of the understanding that had been developed on the theory side that suggested that this particular big D-shaped plasma was the one that had the best overall confinement and stability properties, and would ultimately lead to a more attractive fusion plant. So, we're really proud of the impact the science that's been done here has had on the world. I mean, it's certainly directly influenced the DIII-D device, the way that's come to be. A lot of the underpinnings of the physics there was developed right here at DIII-D, and the institutional experience that we've developed as a result of that. So.
And when you were referring to the D shape, that would be in the vertical direction, with the solenoid being that main kind of flat portion.
So if you imagine that, well, I'm using my hand gestures here.
I know.
Podcast, that's totally useless. But if you imagine that the tokamak as a donut, and if you take a cut through that donut, then that the D is sort of that cross-sectional shape that you would see there, rather than a circle that you might have for a typical donut.
Got it. Yep. Nope, that makes sense. All right, we'll get back on track now.
All right.
So yeah, like I said, you're 1 year into a new role, VP role. What has that transition been like for you? How are things going? Like, I know you've been kind of rolling up your sleeves, getting your hands dirty, and now you've got some other departments and divisions that you are overseeing. What's that been like?
Well, so I mean, it's been excellent, man, and this is really an excellent time for fusion as well. So I mean, nothing but exciting. So within the magnetic fusion energy division, obviously we host the DIII-D National Fusion Program, as mentioned, the largest fusion facility in the US. It's we operate that on behalf of the Department of Energy's Office of Science, and we're very proud to do that. It's really a world-leading scientific platform, and you can imagine it's highly sought by US and international researchers just due to its immense flexibility and control, and the upgrades that we do on it to keep it at the cutting edge, as well as the really comprehensive set of measurement capabilities, which make it often referred to as one of the most diagnosed tokamaks in the world. But in addition to that, we do lots of other things here at General Atomics in the magnetic fusion energy space. We have a world-leading fusion theory and computation department that actually develops a lot of these fundamental theory and simulation codes that we were referring to earlier in our discussion. But really, they range. They've been tuned to a wide range of applications. So there's sort of these high fidelity simulations that might take months of time to run on the, you know, world's fastest supercomputers, but then there's like reduced models that we have that our experimental team might use down at D3D to look at and analyze the shots that we take sort of between shots, and then even more reduced models which can be embedded into the real-time control system that we use to control the plasma. We also have a world-leading engineering and projects department that really is delivering large-scale fusion systems. So we're heavily involved in, you may have heard of the large international collaboration called ITER, which is being built in the south of France. General Atomics actually is responsible for producing the ITER central solenoid, which is a massive superconducting magnet. In fact, will be the world's largest pulse superconducting magnet when it's fully assembled. It consists of 6 modules, roughly 60 feet tall and 14 feet in diameter when it's fully assembled. And this will drive 15 million amperes of current inside of ITER. And each one of those modules uses something like 3 miles of superconducting cable to produce these magnetic fields that ITER will be making use of. So, yeah, we do large-scale manufacturing. We support you know, fundamental theory research. We support.
You guys do small scale manufacturing too, right? Aren't you? You are working on developing the targets.
This is true. Yeah. So that's so now within General Atomics, and we have an what we call our energy division, and that's really focused on sort of both aspects of fusion. So I'm focused on magnetic fusion energy division, but we have a inertial fusion technology group as well. And yes, they produce these you know, very precision targets that are needed for doing the other aspect of fusion, the inertial confinement fusion. So, and you probably know that there was you know, breakthrough results happened at the National Ignition Facility up north in Livermore recently. General Atomics actually supplied the target that was used in those shots. So yeah, we span the range of manufacturing capabilities, that's for sure.
Absolutely. Yeah, so you have the D3D National Fusion kind of facility. You got that kind of ITER manufacturing component. I hear you've also, maybe in the last year or so, been awarded some time on some of the DOE supercomputers as well. So talk to me a little bit about like the advanced computing portion of your field.
Yeah, absolutely. Well, I mean, this has really been, in my mind, fundamental to the breakthroughs that we're seeing in fusion in general. I mean, we're able to simulate with exquisite detail the sort of, you know, what's going on inside the plasma in terms of the transport, the turbulence, and really discovering new things. So, and you really need this high performance and high fidelity simulations to understand some of the coupling, even between like the ion and the electron species, which, you know, when you're trying to simplify models or do, you know, pen and paper type theories, say, well, we'll make this approximation or that approximation. And in most cases, those are pretty good and they work very well, but you can find cases where, you know, that breaks down, and these simulations really lead the way in terms of understanding that. And I would point to that, you know, that again, those great results that we saw at NIF, underpinning those are important first principle simulation capabilities as well. Of course, bringing all of that together right now, many of us at General Atomics are super excited about a new project that we have to design, build, and operate what we refer to as a fusion pilot plant that has the goal of delivering electricity to the grid. And you can imagine this is a huge undertaking that's needed to mature the various technologies that still remain and integrating them all together in a way that can translate into something that will ultimately be economically and commercially attractive. So yeah, there's a lot happening here, and like I said, no shortage of things to keep us excited.
Well, that's, you know, that's a really good point, right? I mean, utilizing the kind of fusion pilot plant project that you just brought up, as you said, there's a lot of involvement in these size projects. How did General Atomics first come to kind of a proposal, given all of the inputs that you guys received, to decide, okay, here's where we're going to start for this style of plant, and here's how we're going to utilize our partners and our in-house engineers and some of the computers that we have access to. Because I'm sure there are just millions of data points that you're having to kind of filter through to even begin such a complex project like this.
Yeah, well, fortunately, we're not starting at this from scratch, right? I mean, General Atomics has been in the fusion game for more than 6 decades, and so we have a preferred approach, a preferred concept that we've been developing here internally for many years, and really with a focused effort for the last few years, in fact. And it's something that we refer to as the advanced tokamak. I don't necessarily need to get into that, but one of the distinguishing features of that advanced tokamak is, you remember when I was describing to you the tokamak, that one of the features of the tokamak is that you've got this central solenoid that you have to ramp the current through. Well, that in a way makes the device inherently pulsed, because you've got to be able to swing flux through that system. And so one of the advantages of the advanced tokamak is that you can find ways to drive the current that you need to provide that other component of the magnetic field through some other external means, or even better, internally, the plasma can drive its own current. We've found ways to do this. So that's the leading approach that we have here, and that's sort of what we've been building our concept around. But there's a whole suite of technologies, of course, that have to be matured alongside just the physics concept that are needed there. And some of these key technologies, of course, relate to developing new materials that can withstand the harsh fusion environment, and another is the technology needed to breed the tritium fuel. So for these fusion reactions we're thinking about is deuterium tritium 50-50 mix, but you need to produce, or you want to produce, that tritium fuel within the power plant itself using a so-called blanket. And we're working on a blanket concept here that marries advanced materials that can simultaneously make the breeding process more efficient, and also potentially open up more efficient thermodynamic conversion cycles. So that's pretty exciting too. So there's a lot of things that are coming together to make all of this happen.
What are some of the aspects of this design that you are most excited about? And think about that in a way of maybe limitations that you are seeing so far that are going to really be challenges that you're excited to overcome.
Well, I think I just was alluding to them right there. So there's really figuring out what the right blanket concept is, and the right way to fuel this. You've got to actually get the deuterium and tritium into the plant itself. And right now we're able to do that on a device like DIII-D by puffing gas in or inject. But it becomes a whole lot more complicated when the plasma gets up to the power plant type densities, and when you've got the size and the temperatures, and so there's a whole, and not to mention dealing with tritium itself. So the whole aspect of how you close that fuel cycle, and what how you do this in a way that's safe and lets you recover the tritium, make sure you don't have a huge inventory on site because that affects how you might license the device, what it looks like in terms of the tritium reprocessing plant that you'll need. The footprint of the facility itself, in fact, can be greatly affected by that. So those are some of the real exciting things that we have ideas that we're pursuing internally right now, in partnership with some of our national lab colleagues, universities, and the like. So
Absolutely. Just out of curiosity, because I know General Atomics has quite a few kind of diverse divisions that all relate back to energy to some degree, right? Unmanned vehicles, I'm thinking. How does General Atomics utilize, or on the other side, silo its divisions for kind of development in one area that can help development in another division or area?
Oh yeah, you're right. I mean, General Atomics works in a lot of areas, including energy, space, defense, and in many of those areas we work and develop technologies in-house from start to finish. And so the energy group, where magnetic fusion energy lives, puts a lot of its own resources in, obviously, to R&D every year. And everyone here is very committed, understands the challenges remaining to support the projects that we're looking at and that can have a major impact. And as a company, of course, GA has a proven track record of bringing this technology from the lab to the field. And this goes all the way back to our early beginnings, where we developed the first inherently safe fission reactors, which were used for training. These were called trigger reactors. More than 60 of these were produced and deployed around the world, and went on to develop commercial fission reactors with what was then called the Atomic Energy Commission. And this has continued through the decades, and with the control systems and magnet technologies, for example, that were developed for fusion, they've been adapted to develop electromagnetic launch systems such as those that GA now deploys, and you can find on the USS Ford, for example. So there's a lot of potential for cross-fertilization and things like that. And certainly the experience that we have with vertical integration, advanced manufacturing, scaling up systems from the lab to the field, making them of production quantities, are all capabilities that GA has developed maybe in the defense space recently that will be extremely valuable to deploying fusion power plants around the world in the future. So, yeah.
Absolutely. With all of that talent, those partnerships, those opportunities, how does General Atomics stay focused? Right? Like how is there, an annual conference of, okay, let's throw all the ideas on the board and come up with kind of the next projects that we want to continue pushing forward with this 6 decades of history? How often do new projects kind of get thrown into the mix that the R&D department gets pushed into that, lo and behold, actually helps some of the existing projects that you're working on? Or more often is the case, I'm assuming, is maybe a sunk cost, and it's okay, we'll try a different project. But I'm just curious how you think about all of the possibilities that are under the umbrella of energy and what to utilize your resources to focus on.
Well, fortunately, we have a lot of divisions which are given a lot of autonomy in terms of, so magnetic fusion energy, I guess we can focus on that, but of course but we get and focused almost to a flaw, you might. I mean, one of the joys of working here is that the people that find themselves in fusion tend to be often referred to them as fusion aficionados or fusioneers. I mean,
fusioneers, I like that one.
Yeah, they got into it because they really believe in the potential of fusion to change the world. And so everyone here is really laser focused on fusion. But of course, different divisions, we meet with other divisions, both within energy, across the broader GA, and strategic offsites and things like that. So we hear about what's going on. Of course, that the owner of the company keeps a keen awareness of everything that's going on. And we'll certainly talk about where there might be synergies or things that can be brought to bear across the company. So a lot of all of that happens very, very organically, but also with particular touch points where these things get brought up periodically year to year.
Very cool. So nuclear is, and I'm of course talking about fission a little bit here, but nuclear as a whole has seen a bit of a resurgence even in the last year or two, maybe a little bit beyond that. But in your eyes, what does the future of nuclear look like for as an energy source for you and General Atomics, but more broadly for the world?
Yeah, well, I think we have to recognize that in some ways the whole energy challenge can be thought of as a national security through that lens, right? And how it relates to climate change, and it really touches everything and everyone. And I think the need for abundant, reliable, clean energy is a real challenge, and one that only continues to grow as the world looks to improve the quality of life for all of humanity. And so ready access to energy is always been that sort of issue of national security. And for me, fusion's unique potential to provide continuous, safe, carbon-free baseload power is, a real strength. And for me, is a reason why I think fusion has to be part of the energy solution going forward. But of course, it's not a one-stop shop. You need all of the renewables, and at least in the short term, fission as well, because we need that capability online today if we want to go carbon free. And I think the other important thing in my mind about fusion is that it can, in addition to, if you want to call it national security, provide economic security also, because it really has a path for providing high tech and high paying jobs for families as we make some kind of transition to this new carbon free type energy environment.
Yeah, I mean, you're spot on. What are some, ideas? I'm sure you've had a couple of ways that folks within the nuclear community can continue to facilitate the discussion of exactly the reasons you just laid out around nuclear and its potential to kind of reshape humanity. What are some, maybe like 2 or 3 discussion points that you might be able to utilize for folks in the nuclear community to really showcase its potential?
Yeah, well, when I think about fusion, I think people should perhaps become aware or recognize of the potential beyond of fusion, beyond just the supplying clean power. And it really has this real opportunity in a way to be done right. I mean, one aspect of that is the fuel for that power is relatively available. It can be made available to sort of all the citizens of the world without reliance on nations that control strategic resources, and really has that, therefore, that underpinning to lead to a more equitable and just future. And while we're doing that, we need to develop a workforce that will mature these technologies that we need along the way, and build and operate this fleet of fusion power plants that we hope will one day power the world. And because we're growing that workforce, we can embrace new methodologies that can really enable people of all backgrounds to succeed in this new energy environment and in fusion in general. And I think, for me, the clean energy revolution, and fusion in particular, can really help lift people up and communities up that have been otherwise left behind. So I think this is an important point for fusion beyond all the technical benefits that you might think about. It's just this fact that we're starting from scratch gives it a unique potential in shaping that future.
If I don't know if you've ever given this any thought, but what other nuclear technologies or ideas are particularly interesting for you? Say you couldn't work on fusion anymore. What other aspects or ideas would you maybe be really interested to go down the rabbit hole of?
That's a interesting question. Like I said, most fusioneers are fusioneers.
I know.
So I don't really think
I'm
that far
sorry.
beyond that. But of course, there's a lot of interesting things happening in the fission space, and I would, and GA is actually heavily involved too. I'm personally not very engaged on that, but there's a lot of work looking at small modular reactors, advanced modular reactors, and GA has some actually quite innovative concepts which they're looking to pursue on that. One of these is actually describes a while back, was called energy multiplier module, which was sort of a modular type system that could be deployed in relatively small units but could be combined together and the like. I think that some of these type of approaches to sort of make better use of the fuel, reuse the fuel through multiple cycles, I think is really critical, so that you don't end up with so much unspent fuel that you then have to figure out what to do with, right?
Absolutely. Wayne, I'd love to give you just a couple of sentences to close out this podcast on just sharing a message with our listeners about nuclear energy, what you're excited about, and how they can get involved if they find this also as exciting.
Okay, well, great. Yeah. Well, I think if you haven't picked up on it, I mean, I believe that fusion generated electricity has the potential to transform the world with abundant clean energy. And I mean, we here at General Atomics have decades of experience really innovating fusion technologies and building and constructing fusion systems and plants. I think we have established strong partnerships with governments, national labs, universities, industries, and really hopeful and optimistic we'll see fusion delivered to the grid on a timescale that matters. And I think if people are similarly interested and motivated in this, they certainly should talk to their local representatives, try to get involved in STEM programs. I know a lot of the universities right now are looking for that kind of, and they're seeing a lot of interest and influx of additional students who want to be part of this. So helping in that sphere, growing new programs, just really expressing that interest and letting it be known that this is the direction we want to go, I think can have immediate impact, because I think the world and the governments are paying attention and want to hear that this is the way forward.
Wonderful. Everybody, Dr. Wayne Solomon from General Atomics. Thanks so much, Wayne. Really
Thank you
appreciate
very much. I appreciate chatting with you, Josh.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.